Has anybody been unable to get this book? A few people. I've heard from a few people. They're still waiting on yours. I expect it'll be available within a day or two. So just do that lab at home. Our other order of business is we've got if you look at our schedule of topics, we basically got today and Wednesday to get through this chapter on calculations. We're really kind of barely started. And then we lose a full class period that next Monday. So we're kind of scrambling already. I have this, if you look at the main page, you see coursework at the top. Go down to quizzes. I can't remember if I had these last time or not. You should be able to see, turn these off. I guess I'll leave them off. But everything under practice for test one, that's what we need to get through today and Wednesday. So I've done some sig figs and some scientific notation. We did the multiplication division rule and the addition subtraction rule in scientific notation. So I think these first four we've done. I'll say reviewing those and just try to push forward to this. So I uploaded this the other day. Just want to open this. So if you look at that slide, I've called it Lecture 1. The first slide is about how do you determine how many significant figures there are in a number you're looking at. The next slide is multiplication, division rule, addition, subtraction rule. I just stuck this scientific notation in there to remind me that that's what I wanted to do next. So we have to start talking about units now. Slide 4, these are the units we mostly use in science. You've probably seen these, especially all of you that raised your hand when you said you took a chemistry class before. Notice we spend most of our time with length, mass, and volume. We'll do amount of substance in moles later. I don't do too much with time. Temperature, I'll go into temperature conversions, but those are very, very simple compared to all this stuff. So I'm going to leave that out for now. This page, okay, page 5. And if you're watching on the camera, on YouTube later, you can't see this, but let me point out. This is just from the chapter E. So it's a subset of what's up here. These were independent, so I'll grab these. You don't have to memorize any of these. I'll give them to you. But notice this. When you're doing conversions, when you're just doing a simple calculation, if you're going, I'll say English, if it's this, both the numerator and the denominator are exact. Did I mention exact numbers last time? Even if you've heard it, I still want to go over it. The difference between exact. It's the opposite of what we look at for significant figures, basically. It's a number that's infinitely accurate. Zeros all the way out to infinity. We call those exact. When you're looking at, so this is pretty much, all this is metric to English. For instance, meters to yards, centimeters to inches, inches to centimeters, kilometers to miles. That's the English system compared to the metric system. That's this, metric to English. So you'll need to remember this because it helps you know what to do when you're making a calculation. English to English, what I mean is 4 quarts equals 1 gallon. What else do we have? 12 inches and 1 foot. When it's English like this, both these digits are exact, meaning you'll probably use it like this, 4 quarts over 1 gallon. And we have to look at all our numerical values and find our significant figures. For English to English, this is infinite. It's 4.0000 all the way out to infinity. And this one is 1.000 all the way out to infinity. Those are the most accurate, those are the most precise numbers. They have the most significant figures in them. That is infinity. They have infinity significant figures.
Excuse me, how do we pull up, like if we wanted to pull up the slide, where would it be at in your slides?
It's under August 22nd, I think, on the left side there.
Yes, sir, thank you.
So English to English, they're always exact. This might make more sense once I do some calculations. And metric to metric is always exact. Metric to metric means 1,000 milliliters is 1 liter. So metric to metric, this is exact. It's really .00000 all the way out to infinity. And this is 1.000 all the way out to infinity. So metric to metric conversions and English to English conversions, both top and bottom are exact. When you're doing metric to English, which is what I'm showing on slide number 5, these are almost all metric to English. I think, so there's miles to feet, that's English to English. There's a couple of small exceptions, but almost all of these are your lengths, your masses, and your volumes. And you don't have to memorize them, but when you're going to make a calculation, for instance, it's so easy to remember. 6.37. That was 1 kilometer. That relationship, and I'm just going to go ahead and write it like this because this is how you'll be using it. Okay. That relationship, 1 kilometer, this many miles, the one, what I'm saying here, the one is exact. Those will all have a 1 on one side of the equal sign and then some messy looking number on the other side. The 1 is exact, and this we have to count for significant figures. So out of the numerator and denominator, for all these different possibilities, only one of these has to be counted for significant figures. The rest are exact and you can ignore them. I mean for the calculation, like calculate this times this times this. Some of those numbers you have to consider for the significant figures. Others are exact and you don't have to consider them. You still have to calculate them. But when you go, okay, now I got to round my final answer to some number of digits, you ignore the exact ones. Because look, this is going to make everything we do one significant figure. I mean, let that be like a hint to you. All these little numbers, the ones, they don't have, this book doesn't have a bank curve for 4 quarts in a gallon, etc. They're not there. But all of those numbers are exact too because it's English to English. So that helps to know when you're going into calculations. So exact numbers. All right, so if you're doing English to metric conversions, if you're doing English to metric, quite how to do this, but if you're doing English to metric, it's one of these on this page, slide. So metric to English and some English to English will be there. But when you're doing metric to metric, you're looking at something like this. This is slide 6. Let me just take a few of these that are the most common that show up. at least in this book. Start with mega. I'm going to insert a row here that's not in that chart called the base unit. Deci, centi, milli, micro, and nano. Okay.
Mr. Everett,
Yes.
I don't think that's on digital.
This slide.
Yeah. Or I don't think it might be on there, I don't know if it's visible.
20th, lecture 1. Look under August 20th and lecture 1.
That was the lecture from last week.
Oh, is it, does it have all the slides?
No, that's just the sick days and science and that issue.
Oh, that's right, I pared that down. Okay, let me upload this, it's better. August 20th. I'm going to delete this first one because it's just a trouble version. Okay, see if that's the right one.
Thank you.
Is that right now?
Yes, that's correct.
Thank you.
Good.
Yeah. Yes.
Go to video for a while. So if you look at that list, you'll see numbers. This one is 10 to the 6, 10 to the 3. I'll say 10 to the 0 here for the base unit. And then deci is 10 to the -1, 10 to the -2. Okay, the first thing to point out, so what you're going to need is some number, a unit, some other unit, a number, and some related unit. You're either probably going to be in meters or milliliters or liters, meters, liters, or I can never say these. What's the third one I keep mentioning? Grams. But let's go ahead and use one of those because it makes this sound better when you say it out loud. Let's say we're in liters. Write those up here. Meters, liters, or grams. Usually. All right, and let's just use meters for now. So if we were talking about meters, we'd be saying megameters, kilometers, decimeters, centimeters. And that's why I like doing this. Capital M meters, km for kilometers, and right here is where we would just say meters. See what I'm saying? Books never include that, but it's part of the sequence here. And now we're going less than a meter, decimeter, centimeter, millimeter, micrometer, and nanometer. So I just like to include this because it helps this discussion. All right, so let's say you have a problem. Convert millimeters to meters. I'm guessing y'all can follow these initials that I'm using, the abbreviations. If you're lost on that, just you have to look at that sheet and it'll show you which ones we're using. So if I had to do this, what I need is millimeters to meters, meaning, actually what I really want is if I'm going to meters, I want meters on top and millimeters on the bottom. need some number there and some number there. And those are the units. So if I see this problem, I can go ahead and write this down and go, okay, that's what I need. I need to convert this that's on the bottom to this that's on the top. Okay, so now you gotta get those numbers. You do it like this. This column, this is really the point. That number in this column is telling you how many meters. And everything from this column is the one. Meaning this, if I'm going from millimeters to the base unit meters, this is telling me that 10 to the negative 3 meters is 1 millimeter. So these are actually referring to the base unit, not their own values. See what I'm saying? 1 meter, and 10 to the 3 meters, 10 to the 3 meters is 1 millimeter. And both are exact. This is the only number here that's not exact. To calculate this out, I would put the 6.34 millimeters, and I'm still going to do this. I like my little one here. Give me a numerator and a denominator.
Would the 10 to the 3 meters or not be 10 to the negative 3?
Yes, it would. Thank you. Yes, I meant for that to be literally this number. I left the negative off. So if you just calculate that out, you'll get the right answer. But notice, I could have used it like this. So 10 to the negative 3, 1, 2, 3, yeah. That equals that. Those equal each other. So either one of these will work and give you the same answer. Also, maybe once you work with this stuff a bit, it starts to seem more natural to you to say 1 meter is 1,000 milliliters. There's 1,000 milliliters in 1 liter. Got 1 liter, 1,000 parts of that for each 1 milliliter. And it does still equal those. You see that? So I tend to like this because it just seems cleaner. That seems messy. Getting powers of 10 messes with my head, but you can do it. You can just plug and chug with that, or that, or that, whatever you like.
So with the one under the 6.34 millimeters, would that just be like your variable that you're trying to solve?
Yeah,
Oh.
that's the random number that some person made up just to invent a problem to convert.
Okay.
Exactly.
Thank you.
And these are very, very standard. They'll never vary. That person being me who made up the problem. So I tend to do this, but realize you can use that. You'll have that list on the test. As long as you can build this out of it and work with the math, you'll be good. Now, I'm about to do my calculation. I've got, this is exact. This one that I stick here, that's always exact. This one is exact, and this is exact because that's metric to metric. So that's the only thing I look at for significant figures. And really, this is so simple, it doesn't look like I'm really doing any math. -3, and my millimeters cancel, I end up in meters. That happens to be in standard scientific notation as it is. So metric to metric conversions. What's next? I didn't really do any English to metric conversion the last time. So I could do some of those. You want to see another one of those?
Yes.
Yeah, let's do some more of those. Yeah, I've got more to explain here. What if your problem what if you needed, so when you're relating to the base unit, this tends to be the simplest possible way it can be. When you're relating between, say, millimeters and micrometers, the most, what would you say, erudite way I think to do this is to relate them both back to the base unit. So if I'm going to do million micro, okay. Let's say I have 37.64 millimeters, and I need to convert it to micro. So the way I do this is I start with milli and relate it to the base unit. So 1 millimeter. 1 millimeter is 10 to the negative 3 meters. It helps to go ahead and put the meters on the bottom based on what I'm trying to do here. And then I'm going to put meters on top here and relate meters to micro. Millimeters to micro. Okay. Let me finish that. So micrometers to meters is, the meters is 10 to the negative 6. I actually did that upside down. So let me swap this. I'm going to flip that over and flip this over. 10 to the negative 3 meters. 1 millimeter. 1 micrometer. 10 to the negative 6 meters. Now it's ready. But notice if I did a little math here, the meters cancel out, and then I do literally have an expression that has micrometers to millimeters. So 10 to the negative 3 meters. Micrometers. 10 to the negative 6 meters. So I've dropped the ones out and I've canceled this M and I've put them both over the same line, over and under the same line. That would work as a conversion for this problem. Did you follow that? When you guys studied this before, did you have a different way of putting it together? If you're happy with the way you do it your way. I'm just showing all the excruciating algebra. But of course, that's not ideal. I've got all these powers of 10, and here's another way you can do it. If you're going to move a power of 10 up to the top, which is basically how we deal with these powers of 10, you change the sign. So I'm going to move that power of 10 up. And that's times 10 to the 6th. I've still got micrometers up there, and I've still got 1 meter down here. Now you know what to do with these, right? Just do the arithmetic for the, what do you call it? Superscript. So that gives me 10 to the 3. That will work too. I could use this to solve that problem. I could use this to solve that problem. I could use that even though it's messier. Or that's the simplest one I have here. But however you want to come up with these, you can use that, you can use that, you can use that. Just make sure you know how to use that chart and come up with the appropriate conversion factor. So I'm going to use the one from out on the end because now it's very simple. Millimeters over the magic line. 10 to the 3 micrometers. Meter. That'll do it. That's exact. That's all our significant figures right there. That's the answer, and it's the significant figures, because the only place we had any significant figures in this problem was here. We built a metric to metric conversion for this, and those are both exact. That's the only number here. This is just a simple unit conversion. So that's the answer. It's not in standard scientific notation. I don't expect you to put it in standard scientific notation unless you're asked to put it in standard scientific notation. You can, but since I tend to do these things multiple choice, you're going to have to find the one that works, and I tend to just leave them like this. But I do expect to make some problems where you do put it in standard scientific notation. So let me show you the twist that shows up. The twist here is we already have a power of 10. And let me move the micrometers out of the way. We already have a power of 10 in this one. If this was just this with no power of 10, I can put it on the slide. This would be 3.764 times 10 to the, to turn this into this, it's 10 to the 1. There's standard scientific notation if there was not a power of 10 stuck on our answer here. We got to the end of our answer, there was a power of 10 here. If you've got a power of 10 and you're going to go to standard scientific notation, here's how I'll tell you to do it. Notice 10 to the negative 4 times 10 to the 4 equals 10 to the 0, which equals 1. And on and on. I can go 5 and 5, 6 and 6, go down to even though. As far as, infinity. So what I do here is I go, okay, how many digits do I have to move this? And I think to myself, it's one digit, so I'm going to go 10 to the negative 1 times 10 to the 1. That is multiplying by 1. So therefore, I haven't changed the value. And now it's just a matter of fixing it up arithmetically. I'm going to swap these two. 10 to the negative 1 times 10 to the 3. If you do this a faster way in your head, that's fine. I'm just showing you all the pure algebra involved.
Wait, so why do we need to do 10 to the negative 1 and 10 to the 1? Like, why do we have to put that in?
We're going to move this decimal point to here to put it in standard scientific notation. But I can't just move it. I have to move it
Yeah.
by doing math. The 10 to the negative 1 is going to cause that to happen. But I had to put a 10 to the 1 to counteract ruining my value with that. You guys following me here?
To move the decimal, you need to multiply it by 10 to the negative 1. By 1 point.
So we solved the problem and we landed here. We already have a power of 10. We're about to put it in standard scientific notation, and we've got a power of 10 in our face. This is how I tell you to deal with it. We need to move the decimal one place, because it needs to be here for it to be standard. So without even thinking, I'm going to go 10 to the negative 1, 10 to the 1. That is multiplying by 1, so I know I haven't changed the value. And the rest is just combining terms here. If I swap these two, that's just an algebraic step. I'm able to, I can put these in any order I want. It's not going to change the value. See what I'm saying? Just for clarity, I'm going to swap these two. I just swapped those two for clarity because I'm going to use these two to do that. Now I've got the decimal where I want. And these, I'm just going to combine those.
So when we're doing conversions, are you asking us to do like all of that?
If it says put your answer in standard scientific notation, yes. If it doesn't, the answer you gave me can still be 100% correct. Standard scientific notation is just a convention we use sometimes. We don't use it all the time. So if you show up with an answer with a power of 10, that's the way I suggest you do it until you're comfortable with it. And then you can think about it however you want.
What would you do here if the number was 700? 376, that would do the 10 to the second, 10 to the next.
You're saying if I had, I go back to my original number. You're saying if I had that
If you had a decimal before this number,
here,
right before the 4.
Between the 6 and the 4.
here, okay.
What would
If
you
you,
want?
if you landed there and you still had that 10 to the 3 on there, that's where we'd be. And I would go, how many places do I have to move this decimal? 1, 2. So 10 to the negative 2, 10 to the 2. Make sense? And I'm going to swap these, but that's just so I can do my negative 2 to this. This will be negative 2. This will be 3. Now these two give me, I still have this left. 5.
So just whatever number you put like 10 to the negative 2, you'll have to put 10 to the positive 2.
Yeah, but it works the other way too. Let me come up with one more example. You're always going to have to do
But it's always going to be like
10 to the
this.
negative something and 10 to the positive something. Do them together, whatever that is. But if you had, and that's where you landed, you could just apply that 10 to the 3. Yeah, don't do that. Make this a little 10 to the 9. Okay. You could turn this into 10 to the 9, but this is where it gets hard to use your calculator, which is why I explained how to do the algebra with the powers of 10. So this time, 1, 2, 3, 3 times 10 to the, but I'm going to put the positive 1 first here, negative 1, because it's this one I want to apply here now. You with me? And now I'm going to swap these two 10s. This is 9 and the other one is 3. And now if I apply that in, I get 3.641. I've still got this 9 minus 3, 6. That would be the answer.
So technically, like, we could just do, like, move the decimal point before, and then just go, like, work backwards to make it standard. Like, you're saying the numbers might be too big to do the calculator?
Yeah, I think what you said is accurate.
Okay.
But I would just say 1, 2, 3. If it's 3, you got to have 10 to the negative 3 and 10 to the positive.
Okay.
And then that's multiplying by 1, and you haven't changed any values. I like to put the one I'm applying here first, but as long as you get the negative 1 and the positive 1. However, whatever number you did this with your finger, that was 3, so I need negative 1, negative 3, and positive 3. So if your answer, you get to the end of a calculation, and there's already a power of 10 there, that's how I tell you to deal with it. You keep your algebra clean, and if you do that, it'll make you get faster at it. You can think your way around it a little better. But that's the word I'm thinking of. Erudite. Okay. Here's another. Here's another conversion from over here. When you have to go across the base unit, meaning I'm comparing, let's say, kilo to nano. So I'm going across the base unit. I still do it the same way. What did I say? Let's do kilo to nano. So I have kilometer, nanometers, or we could be just as easily working in kiloliters and nanoliters, kilograms and nanograms, but I'm just going to keep saying meter. Okay, kilo, back to the base unit. Want this on top. Now, this works out if I do nano first. Nano 10 to the -9 meters to 1 nanometer. And what did I say? Kilo. This is 10 to the 3 meters to 1 kilometer, aka kilometer. So it's the same deal. I just have to mess with all these powers of 10 to reduce it. Actually, I don't have to. I could keep that. I could put 3.78 km right here over a 1, and it would still calculate just fine. But I tend to like to reduce these before I continue with it. Meters is going to cancel. We're going to be left with kilometers to nanometers, which is what we want, kilometers to nanometers. If I move the 10 to the 3 to the top, it becomes 10 to the -3, which means I then have 10 to the -12. And nothing else matters here. If you don't have a number there, you just stick with 1. So I guess I kept this one, but I threw this one away because it's not doing anything. So that's a good conversion unit for this problem. Conversion factor. So if I actually calculate it, why it seems wrong, but I'll find out in a minute. And then -12. Yeah, this is right. Do it. It shouldn't be 10 to the -12. What have I done wrong now? 10 to the -9 meters, and nanometer 10 to the 3. Move the 3 to the top, it becomes -12. Oh. Let's flip that over. What have I done wrong here, y'all? I flip that over. This over 1 nanometer. I need you to flip both of those over. No, still done it wrong. If I flip that one, I did not flip that one.
Hey, Dr. Andrew.
Yeah.
I think you're supposed to divide the 10 to the -9 by the 10 to the -3. For my English. Well, are those all the same problem?
Yeah. All right, give me just a second. It's this. 10 to the -9. Since I'm converting to nano, this is what I started with, and this was wrong. Since I'm going from kilo to nano, I needed to set these up such that kilo is on the bottom and nano is on the top. And I had these flipped over. This has meters where they'll cancel, kilometers on the bottom. If this was nanometers.
Yeah, you're left with nanometer.
But why would kilo be on the bottom if you're starting with it?
Meters should cancel. 10 to the negative 9 meters. Give me a second. I'm ruining the flow here. Meters. Okay, what did you ask?
I was asking, why would you start with kilometers from the bottom instead of like the top? Like, I'm confused why it doesn't go with the cap.
Kilometers has to cancel, and I haven't introduced this yet. So the kilometers has to be on the bottom. And we're converting to nano, so nano needs to be on top. This is right now.
Okay, but how does the kilo cancel? Because
I'm just working out the conversion factor. I
okay.
haven't introduced this yet. You could see this as a problem. Come up with a conversion factor between kilo and nano. Just pretend I haven't done this yet. Sorry. Y'all see what I did? I flipped it over.
Wait, so the bottle or like the little thing in a box is
These,
no, like underneath.
this one,
Yeah, that's like.
this one's wrong.
Okay,
This one, both of these need to be flipped over.
so we're focusing on what's below it.
Yeah, I think that got it. So look here, I just wanted you to see the uncorrected and the corrected. What you're converting to needs to be on top, and what you're computing from needs to be on bottom. And the meters are gonna cancel.
Okay.
This was wrong. Go away. And that means, so if I'm gonna move the 10 to the 9 to the top, it becomes 10 to the positive 9, which becomes 10 to the positive 12. So that's that, and that. The meters cancel. We're left with nanometers over 1 kilometer. That's right. Because there should be a lot of nanometers in 1 kilometer. And then now, I want 1 km bottom to 12 nanometers top. That'll do it. That'll give us 3.678 times 10 to 12. We just landed in standard scientific notation. Sometimes you're just lucky when you land right there on it and you don't have to do anything else. You guys good? I know I made a mess of that. You want me to do another one? Yeah. No?
We'll go over all this information and have a worksheet to go through together. I think it'll be helpful because this is really confusing the first time you see it. So the next, like once you get practicing, it becomes very second nature. So
That's why I put
the
those,
first one's very confusing.
that's why I put those quizzes up, because I want you to go through them and practice them.
Yeah.
I wish I had a lot more of them, so you could just go through as many as it took before you went, okay, I'm cool with this, I got it. It takes repetition. Well, I want to see the problem set up. However, you do it.
It's so funny. She would have
Oh, yeah, that's awesome. It's a different, it's an English. Yeah, it's.
Can I show you all the out? Because what you're doing there is.
That was it. We're gonna break it down. Once you break that, it's just a lot of things, and like, that's like writing something that we may go through and.
It's sort of like what I'm doing on the board.
Show all this stuff. Okay, do that. I understand, I appreciate the process, to break it down.
Like I said, if you understood this before,
Yeah, that's it.
keep the way you've done it. If you get correct answers, you can keep it.
So. I'll show you. It's not.
It's like a-
But it's.
It's just
Do it this way.
I wish I was in the
like all of our neighbors.
I've already opened some new ones. I was like, how do you see it? Were you the only one? We were in your apartment. That was fun. I missed the one down here.
And the sea stars. Yes.
Okay. I'm going to show you this algebra. This isn't really algebra. It's a trick that a lot of people use. We're excited about this one.
Yeah, I love a good trick.
Algebraically, so I've got this set up now. Micrometers to meters, kilometers to meters. I've got it set up now. I've got those two back to meters. You could do this. I'm going to swap this and this. No. I want, yeah, that's right. So I'm going to put 1 kilometer over here and 10 to the -6 meters over here. So I'm going to put this here. I'll put this here. Okay. I should have just moved the number, but those cancel. And we could ignore these.
But you're moving too fast.
Should I start over?
No, you're good. It just was a little too fast.
I myself get confused in the middle of stuff. I don't mind admitting it. I like to catch my mistakes as I go. I started out, if you don't like all this algebra, you like this, but I've got to do it 1 micrometer. Okay, so this one is 10 to the -6 meters is 1 micrometer. And this is 10 to the 3 kilometers. 10 to the 3 meters is 1 kilometer. That's what I've got.
Gotcha.
All right. Now I'm going to swap.
Again?
Well, again.
I thought we swapped the,
This is the way I was doing it before. I haven't shown you the trick yet.
I thought, okay. Confused right now.
I want the meters over each other. I'm going to put the meters together on the right. So that is over here, KM over here. I'm going to put the 1 here. I'm going to put the 10 to the 6 into the -6 here. You see what I did? The meters to the right side. I left that 1 there. That's all I did.
So like,
So it's all equal.
So swap these two.
Swap the units?
So
Swap those
swap
two
the
units. That's what I've done.
gotcha.
But Mars is swapping the units.
This is a trick.
This is.
This shortens the process. And I'm going to put this one over here with the meter. And I'm going to put the 10 to the 3 over here with the micrometer. So what else?
So that is change the numbers on the bottom and change the units on the top?
Yes.
Okay.
Change the numbers on the bottom. Wait,
But change the numbers on the bottom and units on the top.
What?
And your goal.
I'm not going there.
And these numbers that you're swapping, they're those crazy powers of 10.
Okay, right.
Oh, no, they're not. One of them is a 1, one is a 10. That didn't help.
Okay, so the ones meters are lined up.
It's like a puzzle,
It is algebraically fine to swap them.
So then, like, why can't we start out with like 10 to the -6 over 10 to the 3?
I just like to do all the algebra.
So, like,
I mean, put it this way, by the time I'm done with this, everybody will see into it,
Okay.
and then they'll know what we're doing.
okay, like,
You already did it this way though, right? In the past?
yeah, like I understand what you're doing right now, but like on the tests and like labs and stuff.
You
like,
don't have to
we
do all this
show-
on a test. If you know how to get to the conversion factor quickly, just get it.
Okay.
Because you'll most likely be using it in a bigger calculation rather than just. But notice what that did here. Y'all see what that did? It means all of this just cancels and I'm down to just this. Which I was doing the long way before without just swapping things. So this equals. And I can further fix it up by bringing the 10 to the 3 to the top, 10 to the -9.
So the the 1 meter of the other meter, that cancels?
Yep. Once we swapped them, this is 1M over 1M, those just cancel, they're gone.
Okay.
We're left with the units that we wanted.
Now,
Gotcha,
like,
gotcha.
the last two that you have, like, they technically equal each other?
Yeah. Another way of stating that. But this is how you use it, the problem. So if I've got that one over there, so I have this now. So now let's go back and solve the original problem. Micro over 1.
Is that a Y?
Can't read my writing.
She's blind, it's not you.
That's a micrometer, that's a micrometer. It's actually the Greek letter mu. Looks something like that. All right. Now what if this had the very last thing, put your answer in standard scientific notation.
I will take that 10 to the -9 and just add it to the end of the number.
But just make it a negative.
You would
Well,
multiply it by 10 to the.
This is where I've ended. I've already got a power of 10.
Would you multiply it by 10 to the -2?
Yes. And
What?
Should be negative.
yep. Yes, I am going to do it that way. There will be a 10 to the -2, but there should also be a,
So would it, if I was to read 9.948 times 10 to the -1? Or no?
10 to the -7, I think.
Oh, yeah,
Why?
right.
Wait, where
That's
did
why I
you-
do it this way, because
Where
it's
did-
so easy to get it backward.
Where did the 2 come from?
I'll remind you. He's just ahead one step. Hold on. You're not lost.
I am lost. I need to get out.
This answer is fine. That's 100% correct. There's nothing wrong with this. No scientist could walk here and here and go, nope, that's numerically wrong. This is factually the correct solution to the problem. It's just not in that nice, neat, conventional way that scientists like to do. It's not in standard scientific notation. So now I'm gonna put it in standard scientific notation.
Oh, and, okay.
Now it's a separate step.
I get what you mean.
If I'm gonna put it in standard scientific notation, this has to move twice. 1, 2, that's where the 2 came from.
Okay.
Which means I'm gonna go times 10 to the negative 2, times 10 to the 2. See, it's kind of like the way you were doing the unit conversion. She's not listening to me. But there is a very quick way to do this. You just remember, I'm gonna move it back that way, then I gotta add 2 to that, but it's just too much for my brain. I like to get all the algebra out, then I never make a mistake. That's BS, I make a lot of mistakes. All right, let me swap these two, negative 2 and negative 9. And now this gives us 1, 2.
You'd have to still move it, so you're moving it that way. Well, you're taking.
You guys follow that?
I'm confused on how we got negative 7 and why wouldn't it be negative 11? Because we're making it smaller over time.
We do arithmetic here.
But wouldn't that 2 be negative since we're making it smaller? Because if you're saying 10 to the power of 2, you're moving it right to.
The negative 2 is to move the
See, that's why I do it
Okay, I'm
like
gonna
this.
take it.
I put both of these up, so they'll essentially multiply by 1. The problem ended with this as my power of 10.
So you didn't use that denominator.
That was the answer I got to my problem. And then I went, oh, whoops, I've still got to do one more thing. You always do that at the very end if you want to put it in standard scientific notation. And then I looked at this and went 1, 2. So I need times 10 to the negative 2 and times 10 to the 2.
Why?
Because together they equal 1 and I haven't changed the value. But that's a useful bit of algebra to have. Everything's on paper here, nothing's, we're not trying to do stuff in your head. So I put 10 to the negative 2, 10 to the 2. I like to swap these. And then now I'm applying that, and that achieved our goal. We got the decimal where we wanted. That's what this is doing.
Oh, okay.
This is keeping the value from changing.
Okay, I get
But
it.
this achieved that. And then 10 to the negative 9 times 10 to the 2 is 10 to the negative 7.
Yes, sir. Can I write that down? Don't worry.
So whenever you multiply by 10 to a negative power, you would be moving to the left, right? Your decimal place?
When you multiply by 10 to the negative number, you're moving the decimal that way,
All right.
and vice versa. Practice these, y'all. Lucy is eager to help you, so see her if you need to. Meet with me if you want.
I'm sorry, I just need you to repeat something real quick. So the numbers inside of the parentheses, those keep the value the same or the number? Wait. I'm sorry.
That's all right. Here's the process. That's where we landed. I didn't have a unit, believe it or not. You should always put your unit in. And then I look back up here and oh, I've got one more thing to do. The first spot is, what am I doing to this decimal? I'm going 1, 2. So it's going to be times 10 to the negative 2 times 10 to the positive 2. So I'm adding those here.
And then
That ensures that I haven't changed the value.
got you, that's what I was.
The 10 to the negative 2, if I apply that, I get 9.948. But I've still got times 10 to the negative 9 times 10 to the 2.
Okay, that
And then
makes
those
sense.
become the negative 7.
Yes, sir, thank you.
So if you go to coursework, quizzes, here's all the stuff I threw at you guys for practice. these that say practice for test 1, you want to do all of those. Because a bunch of people already did these, I just left them up there, but these are slightly different versions. I played with ChatGPT after Lucy talked about it the other day, and it was great. I got it producing questions, and it's formatted in this crazy way that you can just upload them into D2L and it sets them all up, which that takes forever to do by hand. So I worked with it and got 10 good questions. I was like, okay, now do 20. I did 20. I was like, cool. All right, do 50. And it gave me 50 and I uploaded it. I was like, I got this, man. ChatGPT is gorgeous. Love this. And then I started looking at it and there were mistakes everywhere. ChatGPT will do it correctly, like significant figures correctly. 1, second question, third question, all the way up to like 64, and then the 65th it just completely blows it. And then 67 continues doing it right again, and you can't predict. I mean, it doesn't even sound like a computer. It sounds like a person that makes mistakes like I do. That's what I want ChatGPT for, is to do it perfectly.
So for the practice for test 1, should we save that like to do like the couple nights before, or should we like start doing them as we're like going through classes?
Well, you could do it as we're going through, but I think we've just about covered all this. It's just, I'm going to start reviewing this now so you can see what you want to do for the test. Yeah, these are just for practice, they're not for a grade. But do practice it. My test questions will be just like the questions you see. Let's review a bit and then take a break. Point this at the screen. Camera's acting janky. Got the psychedelic out. Can't even tell. How many significant figures? 4 trailing zeros count. How many here? No zeros. No zeros, so it's easy. It's 5. How many here? 3, because leading zeros don't count. How many significant figures? 4. Not 4. There's no decimal there, so those zeros don't count. It's 2. Same trick here, except this time there is a decimal. That one's 4. How many here? Leading zeros don't count, the trailing zero does, so that's 3. I think you have 10 or 20 of those. Multiplication, division. I think some of these you can answer without calculating, just because you can look at the number of significant digits there. How many digits here? That's 5. 3. So you multiply those together, you've got to have a number that's 3 significant figures. So it's not that one, it's not that one. We have to calculate it out to see which one of these is correct. But you see what I'm saying? It's got to be one of those 2. How many significant figures? 3 there, 2 there. So we need to have 2 significant figures, so it has to be this one. How many here? 3 there, 2 there, so this has to be 2, so it's probably that one. Is it touch screen? This one has two significant figures, so that's got to be the answer. But see if you remember addition, subtraction. So what are we looking for the addition, subtraction? The numbers after the decimal. This one has 1 after the decimal, this has 2, so our answer has to have 1. It's that. 129.1. It's the only one that has 1 after the decimal. Addition, subtraction, how many after the decimal? This one has 2, and that one has 3, so we're looking for one that has 2, so it's got to be that one. For question 6, there's 4 there. Oh, there's nothing after the decimal, so 0 is the number we need to have after the decimal this time. 0 digits after the decimal, not that number 0. This one has 2, this one has 0. So we need one that has 0, it's going to be one of these two, depending on how we round. Make sense? This one has 1 after the decimal, this one has 3, so we need to have 1, it's got to be this one. So look at these and make sure it makes sense to you. Yeah, I need to add some that have you start with a power of 10. If we call these A, B, C, and D, what's the answer to number 1?
B.
4.5 times 10.
You're not multiplying the amount, so if you put how many, you're going to say it. So if you put 4.5 times 2 to negative 3, you're doing this. Is what you're saying. That's why it's positive. You're making it bigger. Yeah.
Wait.
You're trying to get 4.5 times whatever this is.
Yeah.
That equals that.
I wish I had 2 cameras, I could switch back and forth. You had this. Remember that thing where I was saying, oh, we already have power of 10. Here's what you do if you have to put it in the scientific notation. You could still do that. You can do this. There, I have to change the value, so it's totally valid to do that. And then, there's really nothing else to do but to do this. Need to find a better solution to all this. Just so everybody can see. If we got to the end of the calculation and it's just that, there's no power of 10, you could still do what we did before. 10 to the negative 3 times 10 to the 3. That doesn't change the value. That ensures the value stays the same. And now I'm just going to apply that to there. These are not significant zeros, so I'll leave them off. So that trick still works, even if there's no power of 10, for the same reason that it worked before.
If there was a decimal at the end, would you have to put the zeros?
Yeah, exactly. If there was a decimal there, I would put those zeros here because they are significant. That shows 4 significant figures, that shows 4. I guess I'll just keep writing these on the board. 0.056?
3 and then 5, 6.
0.00056. That's all I want. We're gonna have to move 1, 2, 3, 4, so I'm gonna do times 10 to the 4 and times 10 to the negative 4. These two ensure that I'm not changing the value. I'm not changing the order of magnitude. And then this times 10 to the 4, 1, 2, 3, 4, so this turns out at 5.6. And we still have the 10 to the negative 4. You guys okay with scientific notation? And I did go over density last time, didn't I? I did. My classes are all bleeding together. Good notes. Suppose metric conversion factors. Metric, okay. This metric conversion factors. You guys want to do these? This is just saying, come up with the metric conversion factor for whatever. There's not many of these. This again, I did with ChatGPT, and I had to come back and fix it. But these all use base unit, and I didn't realize it was doing that. Could you do these?
Alone?
Yeah.
Maybe.
That's what you're testing when I say practice. Without Lucy, without
I can do this.
random people on the internet. I want to put more in that. What should we do? So this, all right, I'll just say out loud what I'm doing on the PowerPoint. All right, how would you solve this one, this first one? 245 centimeters, what is that in feet? What is that in feet? So here's what you have to look at. Okay, centimeters to feet, what type of conversion is that? Metric to metric? Metric to English. So you would go to this page in the PowerPoint, because this is where all those are. And we're trying to get to feet from centimeters. Up here in the top left, we've got centimeters to inches. Somebody in my other class pointed out that they actually give you this. I meant for there to be one more conversion going on. But if this is on the sheet you're using, you can use this, centimeters to feet. But let me do this a slightly convoluted way so this counts. Pretend we didn't have foot to centimeters. And we had to somehow get the feet from centimeters. Well, you could do this. You get 1 centimeter to that many inches, 39370. I did that backwards. That's inches. And then, so centimeters cancels. And you know what that is. How many inches in a foot? 12. 12. You're happy to answer that one.
Yes, yeah, that's a little bit.
Okay, what here is exact and what is not?
12 is exact.
That's exact. What about this?
Yeah.
What about this?
Yes.
And this?
No? Yeah? No?
It's exact.
Yeah?
If it's not, then we're stuck, every time I put a 1 here, we're stuck to one significant figure every time. Just let that be like a clue to when you're thinking about it. Why is this, why are both of these exact?
Is there equal to each other?
Yeah, that's true. But as opposed to one where one is exact and one is not.
It's like a ratio, right? It's like you have to do
You
it.
can think of it as a ratio.
Yeah.
She thinks one more level above where I'm trying to go. My rule, what was my rule? It tells you when they're both exact.
Every decimal.
Is it English to English?
English to English, both are exact. Metric to metric, both are exact. English to metric, one of them is a 1 and it's exact. The other one is a messy number. That one we have to count significant figures.
Oh, which one is that?
So this was English to English.
Yeah.
This is metric
To
to
English.
English. So that's why that's exact and that is not. And this one's always exact. That's just me sneaking a
Is
1.
that 1 meter? Like
1
the 1 under the centimeter?
What about it?
It doesn't have a unit, and then the one under the centimeter.
Under the centimeter? Oh, this, yeah, there is no unit.
Oh, it's just a unit.
I could do this. 245. And that's how it would be written properly. I just like it to be symmetrical. So I stick it over a 1. I mean, that's true, so I'm allowed to do that algebraically.
If you're solving for those and it's over a 1, you want to multiply across. Like the reason you had it over a 1 is because you're going to multiply it across, like if you're solving.
Yeah, that's why I do
So
it.
it makes it so that there's a top and a bottom for you to multiply and then you divide by the bottom.
I mean, all of that's just true because of algebra. But rather than say all of that, I just do that and it makes it all very obvious that this goes with what's on the top and this goes with what's on the bottom. All right, so if we calculate it, where's my calculator? 245 times 0.39370 and divided by 12. I'm not going to count this towards significant figures, but it still has to be in the calculation. I get. Calculator says 8.038. We're not going to use any of those. 3 significant figures, 5 significant figures. So that needs to be in 3. These we're ignoring now that we're doing significant figures. Those. That's the answer. We happen to be in standard scientific notation. Or I guess we're not using scientific notation.
Because I got, is it 245 or 244?
Holy crap. It's something I know. It is that my dad is in the hospital, but he's okay and stable. But my mom was telling me, what did she say? Our nurse here, he's okay, don't worry. Having blah, blah, blah. One of Daddy's nurses recognized his name and says, "You, Tom, taught her chemistry at North Georgia." My dad has a nurse that was my student. I'm glad my students like me. They'll enjoy my dad. He hurt his back, and he was trying to let it heal on its own. And they waited about a week, and it wasn't getting better, so they've gone into the emergency room, and they'll find out what's going on. He hadn't gotten paralyzed or anything. He's just in pain, and it's not subsiding, so they decided to just go in and get x-rays and whatever they're going to do. asking, eh? I'll text you later. All right, let's do another one. Okay, 2.42 kilograms, we have to get that to pounds. I have to get that to pounds. This question says convert 2.42 kilograms to pounds. That's for the camera. I'm going to go ahead and do this because the camera can't see the problem anymore. And just fill in the numbers wherever I find them. I think we have pounds to kilograms, so we don't have to do 2 more conversion factors. Over here in mass, pounds to grams, kilograms to pounds is right there at the top. 1 kilogram is 2.2046.
Are we gonna have a conversion table on like?
Yes.
the first-
You don't need to memorize anything that's on that slide. I don't think you have to memorize anything that's in this PowerPoint. Maybe those, because the symbols are there.
Do they need to know that, like, for the SI and stuff, like, what we measure things in chemistry for SI units? Like, for, like, in temperature isn't a very.
Oh, yeah. Once we start doing all that, it's kind of obvious that we'll do all this math and all these conversions, and then after the end of next week, we'll never talk again about the English stuff. We're only going to be in metric, so it's going to fade away once you practice all this. So this is set up correctly. Six. I wanted to do some more of these where we do them in standard scientific notation. But this one landed where we wanted it anyway. Okay. It should be obvious what's exact. Take a quick guess what's exact. The ones, of course, those are exact.
2.2046 pounds.
English to metric.
No.
The one does not count, and the messy one does count. The one is exact, and the messy one is inexact. And this is the one that's supposedly been measured, so that one's 3 significant figures. So it's 3, 5, 5. That's the answer. We've even got the decimal where we want it. There's one. The roll of wire has a power of 10. Um, 3.20 times 10 to the 5. Millimeters. What is the length in miles? Convert that to miles. All right. We know we have this much. Millimeters. And we know we have to get from millimeters to miles. So I'm going to write millimeters down here because I know that needs to cancel. I bet I don't have a unit conversion on any of those pages from millimeters to miles. Those are such vastly different numbers. But I'll bet I have meters to miles or kilometers to miles. So I'm going to do this. Millimeters to meters, and then meters to miles. Double. So I need millimeters to meters, a metric to metric conversion, if you're not good with these yet, you'd be having to look at that chart and figure out what it is. I want to use, because that's just the way my brain sees millimeters and meters, 1,000 millimeters in 1 meter. And then that,
Will we ever have to convert anything to miles?
maybe on the test. After this first test, you'll never see miles. It'll all be meters.
Oh, okay, never mind.
1 kilometer, is that what I did, kilometers? No, I did millimeters to meters. I thought there was a meters one here. There's not. The one down here. No. I've got to get from meters to kilometers. And then I can go kilometers, kilometers. So I put both of these conversion factors. This is similar to that complicated way I was doing it that y'all hated so much. But it's just so much easier to build these when you're doing this. Okay, and this is what I found in my list. That is kilometers to miles. 1 kilometer is 62137. 1 kilometer is 0.6237. 0.62137. We'll let the camera people come back in. All right. So I need millimeters to miles. Started with writing millimeters here. I knew I was probably going to have to go from millimeters to meters to get to miles, but it turned out I had to get all the way to kilometers to find something that related kilometers to miles, or related meters to miles. Think you could solve one like this? These are in conversions harder. You can ignore that too. That just has to do with me having to make a whole new batch of these. Having ChatGPT messed me up. The conversions harder. Those you should practice those too. Okay. What's exact here? This is metric to English. So that's exact. That messy number, we have to count those for our significant figures. Metric to metric, those don't count towards significant figures. Metric to metric, don't count towards significant figures. And then we have these three. And that's, of course, exact as well. I'm going to do this. I'm going to split this out. I'm going to take all the numerical values and put them together. I'm just going to start swapping things around. I want the 320, the 1, the next one, and this 0.62137. And then the numerical values on the bottom is 1, 1,000, 1,000. So all the numerical values, next I'm going to do the powers of 10, which really are numerical values, but I'm going to call those powers of 10. I only have one power of 10 anywhere, it's up here. Just put a 1 there. And now I'll get all my units. Millimeters, meters, kilometers, miles. Nothing, millimeters, meters, kilometers. The reason I split these up like this is these you're just going to inspect and cross things off. This you're going to follow the rules for powers of 10, moving things up, doing the arithmetic on the superscripts. And this you're going to do in your calculator. So 3 different ways you're going to go about solving the rest of this. That's why I like to split these out, especially for long ones. Maybe it's because I write a little messy, but my eyes start missing things. So I just make sure I've got everything added back up and its category. We did know at the very beginning we needed to end in miles. So this is really just a double check. We really did know, we were straight up asking. That was our whole point. We spent all this time trying to get it into miles. So we knew this should end in miles. But it's good to do this just to make sure. Because if you don't cancel down to what you expect to, you probably set something up wrong. This is just going to be times 10 to the 5. Put the miles out here. Miles. So we still have a times 10 to the 5 hanging around. And this I'll do in my calculator. This number and this number are the only ones that are inexact, but I do have to make sure to remember to calculate the thousands that are there. 3.20 times 0.62137 divided by 1,000 divided by 1,000. And what my calculator gives me is 1, 2, 3, 4, 5, 5, 1, 4, 9, 9, 1, 0, 6, 8. Of course, I'm not keeping all of that. What did I have? 3 here and 5 here. So it's the 5, 1, 4 I want to keep. 5, 1, but the 9 rounds before up. So 5, 1, 5, and I'll stop there. Times 10 to the 5 miles. That is numerically correct. It's not in standard scientific notation, and we've got a ridiculous amount of zeros here that kind of lend themselves to using powers of 10. But that is 100% correct. But I'm going to do that 10 to the 5, 1, 2, 3, 4, 5. So if I apply that 10 to the 5, I get 0.515 miles. So there's kind of no reason to have a power of 10 here if we get rid of all those zeros. So that's 100% correct as well. These are two 100% correct answers. One of them is using scientific notation, but it's non-standard scientific notation. This one is also in, I guess it's not in scientific notation, it's just written as a regular number. If you needed to put that into standard scientific notation, times 10 to the 1 times 10 to the negative 1. Do the 10 to the 1, the 0. This accomplished the decimal move, and then this was still up. So that's 100% correct as well. If this problem said, put your answer in standard scientific notation, then this one would be wrong, and this one would be wrong, and only this one would be correct. But someone has to specify that you do that. A lot of instructors say at the beginning of the semester, always, 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 put it in standard scientific notation, and then it just covers it, and everyone's supposed to do it. But that's not always.
Why did you multiply the 10 to the 5 by all of the numbers that are on the top, and it was just 3.2 times 10 to the 5?
Well, I want to say because algebra, because I can. I wish I had erased that. Yeah. I think I can rebuild this. And then, what was it? I do want to write this back up there. 3.20 times 10 to the 5. What was that? Millimeters? Millimeters to meters. Meters to kilometers. Kilometers to miles. And something. Six, 2, 1, 3, 7. Okay. Now look at it like this. I have this number times this number, and you're expressly being told that it's that number times that number because of that. This is in some sense this times this. And, you know, in algebra, really, this just goes all the way across. So it's this times 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 this. You see what I mean? So I can move those around anywhere I want. I took the 10 to the 5 off. Who else went that?
It was me.
Oh. I took the 10 to the 5 off because it's a power of 10. And I put it in its own category over here. But I'm free to take any of these, pick them up, swap them. It's not going to change the value of the numerator. So I've got my numerator split up like this. And I've got all my numerical values here, powers of 10 here, and my units here. And I do that because you solve them differently, you handle them differently. Only one of them goes in your calculator, this. This, if we had more powers of 10, there would be something to do here. There were some down here and some to multiply up here. And then those you just cross off and visually inspect. But that 10 to the 5 does conceptually go with this measurement of millimeters. But once we get it all down on paper, it's all just algebra. You can move these around however you want, which is why I do that. Because to me, that's just clears the clutter out and I can see it. But good question. I think we'll do, let's take a break. Want to take a break? We go to 4:50, 4:45. So, do you want to?
Yes.
I thought you wanted to. How long? You back in here at 4?
In an hour?
It's 3:47. It's 3:47 now, right? No, that's not an hour. It's 13 minutes.
I left like 5 minutes